Okay, let's go ahead and start here. We're on our physics book. We're still in unit number 2. Let me just go ahead and backtrack a little bit. I'm going to click on the book so you can see the units. And we've been doing forces at a distance. If you recall, concept 2.1 was an overview of the fundamental forces. And after that, we were going to drill down and look at them force by force. So 2.2, we talked about nuclear forces. And now we're ready to begin with 2.3, electric forces. So we'll go back here and we're going to run right into our Explorer. Notice there's 2 Explore pages, Explore 1 and 2. Today we're going to take care of Explore 1. We'll go ahead and write our Cornell Note template. Make sure you write your date. And we're going to take that essential question straight from the book. How does the electric force relate to the common contact forces people experience each day? You're touching a pencil, you're touching perhaps your notebook or your computer. You have this sensation that you're feeling something, that you're touching something. So, how does electric force relate to that common everyday sensation of touch? Okay. Okay. So let's go ahead and take a moment and just write down what you know. Okay. Go ahead and hit pause. Okay, hopefully you had hit pause on the video and you wrote down a little blurb, a sentence or so, some bullet points, what you know or think about this. And when we get to the end of our notes, we'll write a summary paragraph and hopefully you'll have more information you can add to that. So, Roman number 1, we can see here the electric force. Okay. And they kind of go into this example of the Greeks rubbing some amber, which you guys know is tree sap, right? And sometimes we see fossilized insects and things that are trapped inside this tree sap. It hardens, it becomes a fossil, right? And a lot of times people enjoy amber as a jewelry as well. It's very light and very attractive. Well, anyway, the Greeks found that you could rub amber, and it all of a sudden demonstrated this weird behavior where things would be attracted to it. As you can see in this picture, perhaps a little bit of fabric, wool perhaps, is attracted to that. And this was mysterious to the Greeks. They didn't know what to make of it exactly. But if you take a look in your text there, today, very bottom line here, scientists know that the electric force is behind this phenomena. Okay. And I'm actually going to click on the term force just to continue to remind you that you have a glossary that's available to you. What is a force? An interaction between objects that causes a change to the object's motion. Okay. So just remind yourself every once in a while. It doesn't hurt to click on these and make sure that your thinking is correct. Okay, an interaction between objects that causes a change to the object's motion. Well, in this case there, this amber was able to attract the wool. The wool moved towards the amber, so the term force is appropriate here. So we'll continue to move through here. Atoms are made of subatomic particles. You know that. Electrons with their negative charges, protons with their positive charges. Protons, of course, are located inside the nucleus. In green, you'll see here we've highlighted normally molecules of a substance are electrically neutral because they contain the same number of electrons and protons. That maybe is worth writing down, okay? Normally, molecules of a substance are electrically, and notice how they use that word electrically neutral. They're being very specific here because they contain equal numbers of positively charged protons, right? Protons have a positive charge, and electrons, which have a negative charge. Okay. Now, however, notice in the next paragraph we have this in yellow. However, this balance of positive and negative charges is sometimes thrown off. Electrons may flow away from certain atoms, leaving an excess of positive charge behind, and flow towards other atoms, creating an excess of negative charge. Now, when this happens on a large scale, two objects can become oppositely charged, and that'll produce an attractive force. And conversely, we're just kind of reading down this paragraph. Now, when you have two like charges, you get a repulsive force. Either one is an example of an electric force. Okay. Okay, so we're going to put down number 1 here. This balance can be disrupted. Right? For example, what if you have a balloon, right? And you rubbed it on a person's hair. And what happened was your normal balance, let's just say that we had 4, 5, 6, 7, 8. We had 8 protons, and we had 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay. Well, what happens if all the electrons move to one side? You know, like when you pulled, when you took and rubbed a person's head. Let's just, I guess we'll draw this here. Not a very good drawer, but there you go. You got a person, and this person's got hair, right? Curly hair. and you take the electrons off of their hair, right? You rub it. And what happens is the electrons are added to the balloon. So we add some more electrons here. Okay. Well, when you take the electrons, what happens is they repel all these other electrons over to the other side of the balloon. Because negative and negative, they repel, right? And what happens is that leaves basically all your positives. So I guess maybe I should draw this here. So now what happens is we have this balloon picture. And what you have, in essence, is you have all of your negative charges have been pushed to the other side. And what you have left is all this positive stuff all left behind over here. Okay. And now what happens is this balloon, you basically produce something that looks like a magnet. This is now polar. It has been polarized. Therefore, it will demonstrate electromagnetic properties. I.e., it can be attractive or repulsive. Okay, and that's kind of what they're talking about in that paragraph there. Okay, and these are examples of electric forces. This example. Okay. Okay. And then they go and talk about how you can do this with water, which we've done from time to time. Perhaps you did that in your science class, our science class. There's a lot of ways. Water is a polar molecule, so it's a great way to demonstrate this. Okay, so let's kind of scroll down here. Let's get to the next paragraph here. And it says common contact forces. Okay. We're going to just make this Roman numeral 2. Common contact forces. Okay. In the study of physics, common forces such as a person's push are often called applied forces. Okay. AKA, I guess we could say, AKA applied forces, right? Okay. Contact, because it appears like you're touching something. It appears that you're contacting somebody. When you do a push-up, it appears that you're contacting the floor. You're pushing off the ground. When you shake somebody's hand, or you are playing a sport and you hit a ball or dribble a ball, all these things, it seems like you're touching these things, right? That's why we call them contact forces. But here's the interesting part in yellow. However, when one examines what is happening on the atomic level between two objects that appear to be in contact, it might be surprising to know that there is never any contact at all. Think about that. Wow, there's really never any contact at all. There is never any contact. Instead, atoms of one object are simply coming very close to atoms of the other object. Once this happens, the strength of the electric force becomes very strong between the two objects, therefore they are repelled away from each other. All right, so that right there is the take-home message I think that they're trying to get for us there. Common contact forces are just our imagination. Objects never really ever come in contact with each other. Okay. At an atomic level, as soon as atoms get very close to each other, they start repelling each other. And we should say very strongly, very strongly. This creates a perception that we are touching something, when in reality we are not. Okay. So some pretty interesting stuff there, right? And and then in the next paragraph there, they give a few more examples and they kind of finish off by saying, however, the repulsion from the electric force is so strong that contact cannot happen. Okay. So what I'm going to suggest for you here is watch some of these videos. Just try to make sense of this idea. Okay, so again, we're talking about electric forces, and one very impressive example was this whole idea of touch and how, in fact, electric forces are at play here, and in reality, we are not touching anything. All right, go ahead and let's go ahead and write our summary paragraph here. Okay, so I'm just going to kind of close this off here, and we'll say summary paragraph. And we'll talk to you soon. Take care.